Today we're looking at a paper called Chain of Visual Thought, teaching VLMs to see and think better with continuous visual tokens.
Right. This one is from Yiming Qin and a team of colleagues.
And it really gets at this frustrating paradox you see with multimodal AI. Vision language models, or VLMs, they're incredible communicators, but they often just fall apart on fine-grained visual reasoning.
Exactly. The core problem is that these models lose so much critical, dense, perceptual information.
Things like what, specifically?
Well, think about precise depth, geometry, the spatial layout of a room. All of that gets funneled through discrete text tokens when the model has to think, and you just lose so much fidelity.
Which leads to these, surprisingly bad results on tasks you'd think would be easy, like counting things or telling if one object is behind another.
And that's where the solution of this paper comes in, the Chain of Visual Thought Framework, or CoVT.
So this is designed to bypass that whole textual bottleneck. It lets the VLM reason using what they call continuous visual tokens.
Right. And these are really compact, latent representations. We're talking a tiny budget, maybe around 20 tokens total, that encode all these rich perceptual cues directly into the model's thinking process.
And the results really speak for themselves. This wasn't some tiny marginal bump.
Not at all. Integrating CoVT gave consistent improvements across a whole range of perception benchmarks, anywhere from 3 to, I think, 16%. But the standout was the CV bench depth subtest.
That's the one I saw, a massive 14% improvement.
A full 14%. It really proves that this idea of visual thinking can overcome what was basically a form of visual blindness in these models.
Okay, let's unpack that conflict a bit more. VLMs are, brilliant communicators because they're built on LLMs. But the second you ask them to measure something or position it, they just get clumsy. Why is forcing that continuous visual world into discrete text such a bottleneck?
It's a fundamental mismatch of representation.
Yeah.
Vision is, it's continuous, it's high dimensional. You have this infinite spectrum of colors, distances, shapes.
And language is not that.
Language is symbolic. It's discrete.
Right.
So when you make the VLM verbalize the precise boundary of an object, or that tiny little difference in depth between two things, all that high-resolution visual information gets compressed into nothing. Or it's just lost in translation.
That's a great way to put it. It's like asking a brilliant mathematician to describe a complex equation, but they can only use kindergarten level vocabulary. The tools just don't match the task.
That's a perfect analogy. The model ends up reasoning with abstract words instead of the grounded perceptual reality it's looking at. And this leads to something even more surprising.
It is.
The finding that standard chain of thought reasoning CoVT, which was, revolutionary for LLM.
A total game changer, yeah.
It actually makes visual reasoning performance worse.
Now, that is the ultimate irony. The thing that's supposed to help actually hurts.
Well, if you force the VLM to reason through a long chain of just words for a visual task, any small mistake it makes early on gets amplified.
So if it misjudges slightly closer as behind...
Exactly. That error cascades through the whole reasoning chain. The paper shows it super clearly. Models like Qwen2.5-VL thinking performed over 5% worse than a simple instruct baseline on spatial tasks. The text-only thinking was actively misdirecting it.
So the big question that CoVT is trying to answer is, how do we teach a VLM to think visually, to reason with the same fidelity it uses for language?
And, crucially, how to do it efficiently, in a self-contained way, without having to call some huge external vision API for every single little decision.
And CoVT is their answer.
It is. It injects that dense, fine-grained visual data right into the model's reasoning path. The model learns to internalize perception. It can see and think at the same time, grounded in this continuous visual space.
So let's get into the mechanism. The core is these continuous visual tokens. You said it's a compact representation. Just how compact are we talking?
Surprisingly small. The budget is roughly 20 tokens total.
20? That's it? Why so few?
Efficiency. The goal is to keep latency low during inference. You want the model to generate a quick, compact visual summary, not some massive new image tensor that takes forever to process.
But wait, 20 tokens feels like a tiny budget to summarize a whole complex high-res image. Doesn't that just introduce a new kind of information loss? Why not 50 tokens or 100?
That's the key architectural trade-off they had to make. They found that around 20 tokens was the sweet spot.
The optimal balance between performance gain and efficiency loss.
Exactly. Go too high, and you start losing the very efficiency that made tokens a good idea in the first place. And these 20 tokens aren't random. They're strategically designed. They distill knowledge from lightweight vision experts to encode complementary things.
Like 2D appearance, 3D geometry.
Spatial layout, edge structure, all of it.
So for our more technical listeners, the big deal here is that these continuous tokens are bridging semantic reasoning, the language part, with perceptual grounding, the vision part, and it's all happening inside the VLM's existing autoregressive framework.
Precisely. The model predicts these tokens, which are just highly compressed versions of rich visual data. Then it uses those features in its thought chain. And the really cool part is the interpretability.
You can decode them.
You can. If you want to know what the model was seeing, you can actually decode those tokens back into dense maps, like a segmentation mask or a depth map, and literally visualize its internal thought process.
Okay, so the architecture distills knowledge from 4 different visual experts to cover all the bases: instance recognition, spatial relationships, structure, semantics. This alignment process seems absolutely critical. Can you break down the 4 token types for us?
Yeah, this is where the engineering really shines, because the alignment has to be tailored to what each expert model actually does. So first, you have the segmentation tokens. There are 8 of them, and they're supervised by SAM.
Which is pretty much the gold standard for zero-shot segmentation right now.
It is. It gives you those super high-fidelity, instance-level position and shape cues.
So you're basically teaching the VLM to use its tokens to create the kind of output SAM delivers.
Yes. And because SAM is so fine-grained and task-oriented, these 8 tokens are aligned at the prompt level using the SAM decoder. The objective uses dice loss and focal loss, but there's a critical extra step.
What's that?
They also use Hungarian matching.
Hold on, Hungarian matching. That sounds complex. Why add that? Isn't it crucial?
You hit the nail on the head. It is crucial. It ensures an optimal one-to-one assignment between the model's token predictions and the actual target masks. It forces the VLM to learn how to generate the prompt needed to reconstruct that mask perfectly, not just vaguely.
Okay, that covers 2D shape. What about that 3D blindness you mentioned? How do the depth tokens work?
Right, so next up are the 4 depth tokens. They're supervised by Depth Anything V2, which gives you really robust pixel-level 3D awareness.
And I'm guessing the alignment is similar since it's also a fine-grained task.
It is. Also at the prompt level, using the Depth Anything decoder, they're reconstructed with an L1 loss after this technique called batch matrix multiplication, or BMM, with some intermediate features.
So that BMM step is basically fusing the visual features from the image with the token representations before they hit the decoder.
Exactly. Make sure the features are leveraged correctly to build that depth map.
All right, so that's the fine-grained stuff. What about structure and semantics?
For structure, you have 4 edge tokens. They're supervised by PIDINET, and they capture all the geometry and structural details you need for, say, finding bounding boxes. The alignment here is different, though.
How so?
The tokens themselves are used as a tiny 1x1 convolutional kernel that gets applied to the PIDINET encoder's features, supervised by L1 loss.
Using the token as a convolutional kernel, that's a really clever design. It's like a little lightweight filter for extracting just the structural info it needs.
It's very clever. And then finally, you have 4 Dino tokens for rich semantic info, supervised by Dino2. And these are aligned differently again at the feature level.
Okay, so no decoder this time.
No decoder. They're just mapped to the same shape as the Dino features and aligned with a standard mean squared error objective.
That's a really sophisticated multi-pronged strategy. The big insight seems to be that fine-grained tasks like segmentation and depth need that high-fidelity decoder-based alignment at the prompt level.
Whereas more representative semantic models like Dino can be aligned effectively right at the feature level. It shows they really thought about how each expert encodes information. You can't just treat all 20 tokens the same way during training.
Okay, so let's move on to the training itself. It's not like you can just throw these tokens in and hope for the best. The paper lays out a 4-stage progressive pipeline to teach the VLM how to actually use them.
Absolutely. Think of it like learning to drive a race car. You don't just jump onto the track. You start with the basics, then you practice specific moves, then you integrate it all, and finally, you learn to be efficient.
So what's stage 1, the basics?
Stage 1 is just comprehension. This is just teaching the basic token vocabulary. The visual tokens are inserted right after the image tag, and the VLM just has to learn what a depth token means in context.
So you go from that passive understanding to actively using them.
Correct. Stage 2 is generation. Here, they change the Q&A format to explicitly tell the VLM to generate the tokens. Something like, based on the image, generate the segmentation, depth, and edge map tokens.
So you're making sure the model has the mechanics down.
Right. And then stage 3 is where the magic, the actual thought chain happens.
Reasoning.
That's it. This introduces the chain of visual thought format. The tokens are now inserted inside the think tag, guiding the model to use that visual data to get to the final answer. So for a counting question, it might generate the segmentation token inside the thought block. It's mentally segmenting the image before it gives you the number.
It's forcing the model to visualize the steps, not just narrate them.
Exactly. And then stage 4, which is so important for real-world use, is efficient reasoning. In this stage, they randomly drop subsets of the visual tokens.
Why do that? Why is the random dropping so important?
Because it forces the VLM to learn to use only the features it actually needs for a given task. It stops the model from getting lazy and relying on the full set of 20 tokens every single time. If the task is just 2D counting, it learns it doesn't need to waste compute-generating depth tokens. It promotes modularity.
Okay, let's talk proof, the quantitative results. How did CoVT actually solve tasks that stumped strong baselines before? We need to put these numbers in context.
The results, with Qwen2.5-VL as the backbone, are really compelling. The overall gain on CV bench was a solid 5.5%, but the real story is in the subtasks.
The ones that target perception specifically.
Right, a massive 14% gain on just the depth subtask of CV bench. And HR Bench 8K, which is all about high-resolution understanding, saw a 4.5% gain overall.
And to put that 14% gain into context, that's the difference between the model basically guessing at spatial problems and actually getting them right. It's seeing a clear distance, not just a vague shadow.
Precisely. And when you compare it to other latent token approaches, CoVT really pulls ahead. With depth tokens, it beat a model called Aurora Depth by almost 13% on relative depth.
Wow.
And with segmentation tokens, it beat Aurora Count by a staggering 26.6% on counting tasks. It's clear validation that using these continuous tokens for thinking provides much better grounding.
Let's also hit the key ablation studies. They really show why their specific choices for alignment and tokens were so critical.
The ablations were crucial. First, they just confirmed again that text-only 2T hurts vision performance. You need these visual tokens. Second, the alignment strategy is non-negotiable. Direct feature alignment just didn't work as well as their tailored decoder-based approach.
Why is that distinction so sharp?
Because direct feature alignment is simpler, sure, but the tailored decoder-based method, especially for SAM and depth anything, forces the VLM to learn the specific output structure of the expert. It captures those fine-grained cues way more effectively than just matching internal feature vectors. They also found that 8 segmentation tokens was the sweet spot for performance versus load.
Interpretation is always tough with latent spaces, but the fact that you can decode these tokens gives this incredible window into the model's head. Can you walk us through one of the examples that shows this visual thinking in action?
Figure 5 in the paper is perfect for this. Take the example where it's asked about the relative depth between some books and a chair in a room. The baseline model, Qwen2.5-VL, it got it wrong. It claimed the chair was closer.
A classic grounding failure. What did the CoVT model do differently?
It used its perceptual memory. Its thought chain first generates the depth tokens, giving it a clear, grounded depth map of the whole scene. Then it uses its edge tokens to highlight the boundaries of the specific objects, the books and the chair.
And with that evidence,
with that combined perceptual evidence right there in its thought chain, it can correctly determine that the books are in fact closer. It's using grounded visual facts, the decoded maps, to overturn the baseline's linguistic mistake.
that's the difference between guessing based on, I don't know, general knowledge that chairs are often in the foreground versus actually looking at the evidence. This paper really provides a clear path forward for VLM development.
It does. CoVT successfully moves reasoning out of the discrete, limited space of language and into the continuous, dense space of vision. And we have to stress, this specialized skill doesn't hurt its general abilities.
Right, it doesn't come at the cost of generalization.
The paper shows it's still competitive on general non-vision benchmarks. It even saw a small 1.2% improvement on those, so there's no catastrophic forgetting.
That's so important for deployment. You don't want your new depth expert model to suddenly forget how to summarize an article. But the authors were also clear about limitations and future work.
They were. One thing they acknowledge is that they haven't fully explored the design space for visual experts. They picked 4 very strong ones, but there might be even better combinations out there. Or maybe new specialized tokens like velocity tokens could expand its capabilities.
And what about that true multimodal reasoning, the seamless blending of thought?
That's the other big one. The current framework still operates in phases. You generate the visual thought, then you generate the text answer. It's not yet fully interleaved reasoning.
So no seamless dynamic blending of visual thoughts and text thoughts in one continuous chain.
Not yet. That kind of moment-to-moment switching between representations. That's the next big frontier for this research.
Which brings us to our final thought for you to take away. Since CoVT proves so decisively that reasoning in a compact, latent visual space is incredibly effective for grounding fine-grained perception, the key challenge now shifts to dynamic control. So how can we build a unified end-to-end framework where the model itself decides in real time whether it needs a text thought from the discrete symbolic space or visual thought from the continuous perceptual space to achieve the best accuracy and efficiency for whatever task is right in front of it?